In this video, I will show you how you can calculate the eigenvalues and eigenvectors of a 2 by 2 matrix. You can easily extend these results to an n by n case. So let's start with a simple matrix. Let's assume A is equal to 2, 1, 5, and 6. And we want to find the eigenvalues of this matrix. Now, there is this wonderful formula which states that if we have a matrix A, the eigenvalues, denominated lambda, can be found if we subtract from A the identity matrix times the vector of eigenvalues and take the determinant of that expression, which has to be equal to 0. So we can apply this formula to this matrix. So let's first write down the expression in here. Given that it's the identity matrix, we can very simply and nicely write this as one matrix. In particular, we'll have 2 minus lambda, 5, 1, and 6 minus lambda. And we know that if we take the determinant of this matrix, this must be equal to 0. But we can also write out what this determinant actually is. This determinant is actually 2 minus lambda times 6 minus lambda minus 5. Now, we can multiply this out, and we would get 12 minus 8 lambda plus lambda squared minus 5 must be equal to 0. So what we can do is we can subtract 5 from here, we're left with 7, and if you look very closely, you can transform this expression into a nice 2-bracket expression with 1 minus lambda times 7 minus lambda. And we just found our 2 eigenvalues. Because this expression has to be equal to 0, so either this part has to be 0, this part has to be 0, and for this to be true, we have the first eigenvalue equal to 1, and the second eigenvalue equal to 7. So how do we find now the eigenvectors? There's a second formula for that, and that's the basic property of eigenvalues. In particular, we know that A minus I times lambda, so the identity matrix times lambda, times an eigenvector corresponding to the eigenvalue here has to be equal to 0. This is by the basic property that the vector times the matrix has to be equal to some eigenvalue times that vector. So, if we calculate that expression in the middle, we can easily calculate the eigenvector we need. So, let's calculate this for the first eigenvalue. So the expression we get for lambda 1 will be 2 minus lambda, which is 1, 1, 5, 6 minus lambda is 5. We end up with this matrix times some vector, the corresponding eigenvector is equal to 0. Now, if you look closely, you might be able to see that this times 5 will give you the same as here. So you can have an eigenvector of the form v1 is equal to 5 minus 1. And multiplying this v1 times this matrix will give you 0, or the 0 vector. Now, if you look here at this expression, you can multiply both sides by any number you like, and it still has to hold, which implies you can multiply this vector by any number you like, and the expression has to still hold. So let's find the second eigenvector, v2. So for v2, we again write down the matrix. This time we have to subtract 7. So 2 minus 7 is minus 5. We have still 5 here, we have still 1 here. 6 minus 7 is minus 1. And we need to have this expression to hold. Again, if you watch closely, you can see that these two are just the same number, but with a minus sign. So if you multiply the vector 1, 1 times this matrix, you will get 0, 0. So our v2, our second eigenvector, is equal to 1, 1, or any multiple thereof. Now if you're not sure how to get, or if you don't see immediately how to get to the eigenvector, you can also write this down as a system of equations and solve it. Just note that the zero vector is also a solution, but to find the eigenvectors, you must exclude the zero vector. So let me give you another example which makes it much easier to calculate the eigenvalues, but potentially much harder to calculate the eigenvectors. In particular, let's take the same matrix, but replace this 5 here with a 0. Now we have a triangular matrix. If we calculate the determinant of this triangular matrix with this adjustment mate, we will get the determinant of 2 minus lambda, 0, 1, 6 minus lambda. Right? But if we calculate that, which has to be equal to 0, we simply get 2 minus lambda times 6 minus lambda. Wait, we just calculated the eigenvectors. The eigenvalues for that. So we have lambda 1 equals 2 and lambda 2 equals 6. And we calculate our two eigenvalues. So all that's left is we need to calculate the eigenvectors. So we do the same we just did. So for lambda 1, we look at the matrix, and we have 2 minus 2, 0, 0, 1, and 4. Times some vector. The eigenvector 1 has to be equal to 0. Now we have a problem. If we have something that works here, are you sure it works here? Well, either you solve this as a system of equations again, or you see the simple solution, which is the top equation is always satisfied, so we just need to satisfy the bottom equation. In that case, we have a similar case to what we had before with 1 and 5 on both sides. So we just need the vector 4, minus 1. And we have our first eigenvector, which will be 4, minus 1. If we do the same for lambda 2, that is the second eigenvalue, which was 6. So we subtract that, we get minus 4, 0, 1, 0. Now we have zeros here. But this immediately allows us to find a very simple vector that satisfies this equation. Because minus 4 times anything will never give us 0 unless that's 0. So we can immediately see that v2 has a 0 on top. But on the bottom, it can be anything, because anything multiplied by 0 will give you a 0. So we have a simple vector 0, 1, or any multiple. Thank you for watching.